Okay, so week 4, day 1, as I was starting to go into that, we're taking kind of a turn from what we went over last week, and the week prior. We were doing a lot of OOP, with Python, for the previous few weeks, but now we're going to have like a week break where we're revisiting, data structures and algorithms. We did a little bit with this back when we were doing our, review for Python and JavaScript. But now we're going to go into a few more advanced concepts that are good to knows. You probably won't use it a ton, but definitely should be familiar with this. And like I said, off recording, if you're looking at applying to one of the FANG companies, then you absolutely need to do some additional study on this, probably with another um, module or something outside of our program as well. But let's dive into this. We're going to look at logarithms and big O notation. What is this even used for us? Well, it's just kind of to help us analyze the performance of our algorithms, to understand like how they will perform as the inputs increase, as their input size grows. So we're interested in making sure all of our algorithms and our programs run as smoothly as possible and use as little memory as they need to be able to complete the objective. Real world example, I wrote a report the other day that had to pull the last 30 days of forecast data submitted from multiple different areas in our grid. And they submit hourly every day, and there's multiple different forecasts underneath each of theirs. It's just a ton of data coming in. So when I write an algorithm that is very implicit and, it's doing for loops and then it's looping through other stuff underneath, it seems like this will be okay. I can write it like this. It will complete just fine, right? The computer can absolutely run through all this data without issue. No, when you do something like that and hit your run, all of a sudden, 6 hours later, the server is still processing through all that data. It's still working on the code. When you're working with that much code in your actual job after this, one, the way you write your algorithms and applications will definitely affect the runtime of those. So learning how to kind of analyze that ahead of time, so you're not spending time rewriting and trying to make them run a lot faster. Once I rewrote it with definitely a better approach, I got that down to a 6-minute runtime. So what took hours before, I was able to cut out a ton of runtime, both through changing my SQL queries as well as the way I was handling the data in pandas, and drop that down to like 6 minutes. So that is important and something we can go ahead and analyze ahead of time with this big O notation. First, before we look at big O notation, though, we're going to learn about logarithms, which is kind of the context of big O notations. So I, I'm not going to put this in the text pad. We'll just look through the README and try to understand this together, because it's going to look the exact same in the text document I have behind. But everybody knows exponents, right? 2 to the power of 3 equals 8. We're pretty good with exponents. That's a pretty basic math expression that we should all be somewhat familiar with. Logarithms are basically the way to find the exponent when the result is known. So instead of solving 2 to the power of 3 and then trying to solve that, we would have the 8 and try to figure out what power we're raising to. And that's what a logarithm would do for us. It kind of is that backward, a reversal of this to go ahead and try to figure out the power or the exponent that would result in the answer that we have provided. So in general, it will always follow this structure. If we have, I guess this is, I don't know math variables and why we choose the letters we choose in these, but if we have b raised to the y equals x, then the log of b, x equals y. So y now is, the exponent value we're trying to solve for, so that's why it's at the end now. X is the answer that we have from that, which is right here in the equation, and log of b is just what our given base is. So to help visualize that, here we see 2 raised to the 4th power is going to equal 16 with all these steps in between. Now, if we try to rearrange it into the logarithm to figure out, if we didn't know this 4, if we had like an x here, 2 to the what power equals 16, we would write log of 2 base 2, because that's our base number there, for a result of 16 is equal to what power? And that gives us 4. So you would figure that out by just, as we see here, base 2, the logarithm with a base of 2, with an answer of 128. We just kind of figure out how many times we need to multiply it together to reach that answer. And so here we can see we do 2 multiplied together 7 times to reach that answer. And that's how we figure out the answer to our logarithms. Any questions on that so far? Are we tracking? We're following along how to take from our exponential values here to using a logarithm. Okay. We're just introducing you to this only because big O notation does kind of use logarithms. Well, it doesn't kind of, it does use logarithms in its algorithms. As we can see in the README, a lot of times it's because many of these algorithms are repeatedly divided by 2 throughout the algorithm, leading to this logarithmic complexity. So like a binary search, which I don't know if we've went over these yet, binary search, that might be in this week. You're going to look at binary search. You're doing a few different search algorithms later this week, but in that one specifically, the search space is halved each time, right? So you usually start with like a full list, and then when you do your binary search, you'll break it up and search into 2 lists. You'll like break it in half and search in those. Then you'll keep breaking them in half until you reach the number you're looking for. We're going to look at this time complexity thing further down. We're not going to do that now. So key takeaways, we see that logarithms are the inverse operation of exponentiation. So it's kind of the way to figure out the exponent when we know the base and the result of that. And then in context of algorithms, big O notation, base 2 logarithms are commonly encountered. Yes, okay, so we use that a lot in our big O. Okay, so big O. What big O is established by assessing like the worst case of an algorithm's performance. So it gives you, we'll just end it there. It's the worst case example. If an algorithm is said to be O(n) squared, it means that the algorithm's complexity will not grow faster than a quadratic function, even in the worst case scenario. Just reiterating the same thing. It's a worst case understanding of how our algorithm will perform. And thank you, Logan, for popping in chat an example to help kind of wrap your head around this. We will get practice today, kind of figuring out logarithms. Don't know how hands-on you'll be with logarithms in this course, but it's good to know. So big O, it's the worst case scenario of our algorithm. It's going to tell us, worst case, how long will this take to run? And kind of give us an idea on if we increase input into that, how our time will increase as a result as well. So we have two different ones we're focusing on today. There is constant time, which we commonly see written as O1, and then there's linear time, which is ON. And for constant time, basically the runtime and space requirements, all that will remain constant regardless of the input size. So the algorithm is not influenced by what you are passing in as the input. If that seems obscure and you can't wrap your head around it, here's a nice example. So accessing an element in an array, I can change the size of this array that I'm passing in from like just one value to like 10,000. I can increase that size, but every single time this runs, it's only returning one value every time. Doesn't matter how much I increase this input, it's always going to return one thing in it. And it always goes to that one spot. There's nothing happening in between, right? There's no looping through a list or anything. It's just taking in this input and going to one direct value. If there was some things happening within this function, then it would change its O notation. But in this example, it is simply taking in an array and going to one value, and that's it. So that's what we mean by constant time. Any way we try to influence the input will not change the performance of this algorithm. And then the other one we'll look at is linear time. This is ON, is how it's usually written out. And this grows linearly with the size of the input. So as the size of the input increases, then the space or time it needs also increases linearly. So if you imagine that graph, it's just going to be a straight line up. It's a very static increase, thus the linear. Here's an example of that here. So this is going to sum elements in an array, I assume, because they named their function very well, so I can grasp what this is doing. We start with a total equals 0, and then here we're iterating through 4 number in this array. We're going to just simply add that number to this total, this running total. And then we're going to return that total at the end. So with this, if we think about it, if we're passing in an array with one element, it's going to come in here and it's going to run through this for loop once, right? It's going to run through it once and just add that to this total and then done. If this was a constant time algorithm, I would expect when I passed in 2 values in the array for this to just run through this loop once like it did before and be done. But that's not the case, right? Because now there's 2 items in the array. It's going to run through it once, but then it's going to loop back around and run through it a second time, right? So now for 2 items, we have it running through this loop 2 times. So that's where we see this kind of linear thing. Like it's a direct correlation between the number of inputs we pass in this array and how many times this for loop is going to run in this function. So that is a linear time. You can expect the amount of time and space for this to complete to increase, the same amount each time you add a new element to this array. So comparison, let's see, this constant time remains constant, unaffected by input size. It's efficient with a fixed runtime, just accessing a specific element, whereas linear time will grow with the input size. And this is a very common one. Like, think about it. Everything we write is pretty much a loop that iterates through something, right? So every time you iterate through something, that's going to be a linear time O notation, because it clearly depends on how many things we have in the input for that loop to run through. And once again, just reiterating everything we literally just walked through. So like I said, super short lecture today, just very minimally introducing these concepts and scratching the surface of logarithms and O notation. I know it was super short and sweet, but does anybody have questions on kind of these two concepts? And specifically this constant versus linear O notation, or any questions about why we're even doing this? I mean, it kind of explained at the beginning. You'll realize when you start working in it. Obviously, I'm not the best at O notation. Otherwise, I would have done this ahead of time with that report function that I wrote that took 6 hours to run. So, very useful thing to go ahead and grasp and pay attention to when you're writing your own code. All right. Well, if we don't have any questions on this, I guess I could stop recording and we can go over what your challenge is for today. Thought I
I
was
have a
going to
thing
write
in
out more
chat.
things. Oh, sorry, go ahead.
I have a picture up in chat that kind of goes over this. It's the last link.
Oh, you're going to see this tomorrow.
Oh,
And so when I looked at this lecture today, I was looking like where's the rest of the O notations that y'all should be going over? Because obviously, look, these are um O, here's the ON, right? That's the or the linear, and then O1 is the constant. Not the only two on this little graph. Tomorrow though is when you're going to dive deeper into the different types of O notation, not just the two I briefly introduced you to. You're going to look at more of these and how to actually analyze functions for which one it would be. So that is tomorrow. But good, this is a very good visual, right? See, input size. This, as the input size increases, the time does not for our constant O notation. But for a linear, it's a 1-for-1. As soon as I add something to that input, the runtime also increases proportionally. It is a very, very good graphic. Thank you for sharing. Any other questions or comments or resources y'all have found in your own? No? Okay, I will stop recording and we will go over your challenge for today.